Welcome to this problem walkthrough. Today, we will explore LeetCode problem number 1197, titled Minimum Night Moves. This is an exciting problem that challenges us to calculate the shortest path a knight can take on a chessboard to reach a specific destination. Let's dive in and uncover the best approaches. In this problem, we are tasked with determining the minimum number of moves a knight needs to reach a specific target position on an infinite chessboard. The knight starts at the origin, which is the point 0, 0, and must move to a target position x, y. Now, recall that a knight in chess moves in an L shape. This means it either moves two squares in one direction and then one square in a perpendicular direction, or one square in one direction and then two squares in a perpendicular direction. From any position, R, C, the knight has exactly 8 possible moves it can make. These are listed here, such as moving to R+2, C+1, or R1, Sin2, and so on. Your goal is to determine the minimum number of such moves required for the knight to reach the target position x, y. The input to the problem consists of the integers x and y representing the target coordinates, and the output is a single integer indicating the minimum number of steps required. To better understand the problem, let's look at some examples. In the first example, the target position is 2, 1. Here, the knight only needs one move to reach the target because it can move directly from 0, 0 to 2, 1 in a single L-shaped step. Therefore, the output is 1. Now consider another example where the target position is 5, 5. This case requires more moves since the target is farther away. We'll see the explanation for this scenario next. In the example where the target is 5, 5, the minimum number of moves required is 4. One possible path the knight can take is as follows. It first moves from 0, 0 to 2, 1, then from 2, 1 to 4, 2. From there, it moves to 3, 4, and finally, it reaches the target at 5, 5. This shows that even though there may be multiple paths to the target, the minimum number of moves required in this case is 4. Now, consider another example where the target position is in the negative quadrant, specifically, -2, -3. When the target position is -2, -3, the knight still follows its L-shaped movement, and the solution takes into account symmetry in all directions. One possible path for this case is, the knight first moves from 0, 0 to -2, 1, then to 0, -1, and finally to -2, -3. This requires exactly 3 moves, so the output is 3. The problem also has some constraints and edge cases to consider. For example, if the target is the starting position, 0, 0, no moves are needed, and the output is 0. If the target is close to the origin, like 1, 1, the knight may require multiple moves despite the small Manhattan distance. Additionally, the solution must efficiently handle large inputs, such as when x and y are as large as 300 or as small as -300, given the constraints. These edge cases test both the correctness and efficiency of your solution. To solve the problem of determining the minimum number of knight moves to reach a target position on an infinite chessboard, we first consider a brute force approach using breadth-first search, or BFS. This method is intuitive since the problem can be visualized as finding the shortest path in an unweighted graph, where each valid knight move represents an edge. Starting at the origin, which is 0, 0, we explore all possible moves layer by layer using a queue, ensuring that we keep track of visited positions to avoid redundant calculations. At each step, we generate all 8 possible knight moves from the current position and add them to the queue if they haven't already been visited. The process continues until we reach the target position, at which point we return the number of moves taken. However, while BFS guarantees the shortest path, its performance can degrade significantly due to the infinite nature of the chessboard. Exploring positions far from the target wastes computational resources, making this approach inefficient, especially for distant targets. To address the inefficiencies of brute force BFS, we can optimize it by leveraging the symmetry in knight movements. On a chessboard, the minimum path to any position x, y is equivalent to the path to x, y. This means we can effectively reduce the search space to the first quadrant, where both x and y are non-negative. By transforming the target position to its absolute values, we simplify the problem without losing correctness. From here, the BFS process remains largely the same. Starting at the origin, we explore valid knight moves iteratively, ensuring we only traverse positions within the reduced search space. This optimization significantly improves efficiency by reducing the effective search area by a factor of 4, making it well suited for larger target positions. The time and space complexity remain quadratic in terms of the distance to the target, but the reduction in unnecessary computations makes this approach much more practical. Another strategy worth considering is the A** search algorithm, which uses a heuristic to prioritize paths that are likely to lead to the target more quickly. I** combines the number of moves taken so far with an estimate of the remaining distance, guiding the search toward the goal in a more focused manner. Here, the heuristic is based on the Manhattan distance to the target, divided by 3, since a knight can cover at most 3 units of distance in one move. Using a priority queue, we expand nodes with the lowest combined cost, adding their valid knight moves to the queue as we progress. While the worst-case complexity remains quadratic, the heuristic often allows A** to explore fewer positions compared to plain BFS. However, this approach requires careful tuning of the heuristic. If the estimate is inaccurate, the performance can degrade to that of regular BFS. Additionally, A** is slightly more complex to implement, making it less appealing as a general solution for this problem. After evaluating the different strategies, we chose the optimized BFS with symmetry reduction as the most suitable solution. This approach strikes an excellent balance between simplicity, efficiency, and robustness. By leveraging symmetry, we reduce the search space significantly, and the BFS framework guarantees the shortest path is found. While A** can sometimes outperform BFS due to its heuristic-driven exploration, it introduces additional complexity and relies heavily on the quality of the heuristic, which can be difficult to fine-tune. On the other hand, the brute force BFS was ruled out due to its inefficiency in handling the infinite chessboard, as it wastes resources exploring unnecessary regions. Ultimately, the symmetry-optimized BFS offers a straightforward implementation that works efficiently for all possible inputs, making it the most practical and reliable choice for this problem. To solve the problem of determining the minimum number of knight moves required to reach a target position on an infinite chessboard, we can model the chessboard as an unweighted graph where each position is a node. The knight's unique L-shaped movement allows it to jump to one of 8 possible positions from its current location. Given that we are tasked to find the shortest path from the origin to the target, breadth-first search, or BFS, is the optimal choice. This is because BFS systematically explores all nodes at the current distance before moving to the next layer, ensuring the shortest path is found. To begin, we initialize a queue to handle the BFS traversal. Each entry in the queue consists of the current position of the knight and the number of steps taken so far. Additionally, we use a visited set to track positions that have already been processed, preventing redundant calculations. The starting position, 0, 0, is added to the queue with a step count of 0. We also explicitly define the 8 possible knight moves as coordinate offsets to streamline the traversal logic. Once the BFS is set up, the actual traversal begins. While the queue is not empty, we repeatedly dequeue the front element, which represents the knight's current position and the number of steps taken to reach it. If the current position matches the target, we return the step count immediately since BFS guarantees this is the shortest path. For every potential move the knight can make, we calculate the resulting position by applying one of the predefined offsets. If this new position has not already been visited, we mark it as visited to avoid processing it again in the future. Then, the new position, along with the increment step count, is enqueued for further exploration. The process continues until we dequeue the target position, at which point the result is returned. This approach leverages the systematic nature of BFS to ensure that the first time we encounter the target, it is with the minimum number of moves. There are several key insights that strengthen our understanding of this approach. First, BFS is particularly well suited for this problem because it processes all positions reachable in K moves before proceeding to those that require K+1 moves. This guarantees that the first time we find the target, it is along the shortest path. The use of a visited set is equally crucial, as it prevents revisiting positions we have already processed, ensuring efficiency and avoiding unnecessary computations. Although the chessboard is conceptually infinite, BFS dynamically expands the search area based on the target's location. This means we do not need to define explicit boundaries. Moreover, the algorithm can be optimized by taking advantage of symmetry. Since night moves are symmetric across the x and y axes, we can reduce the target coordinates to their absolute values. This allows us to treat all quadrants of the chessboard equivalently, further reducing the effective search space. The data structures used in this algorithm play an essential role in ensuring its correctness and efficiency. The queue is the backbone of the BFS traversal, maintaining the order in which positions are processed. Each entry in the queue consists of the current position and the number of steps taken to reach it, ensuring the traversal proceeds layer by layer. The visited set is another critical component, as it ensures that each position is processed at most once. This prevents infinite loops and reduces redundant calculations, significantly improving performance. Additionally, the list of predefined moves simplifies the generation of new positions. By storing the 8 possible knight moves as coordinate offsets, the algorithm can efficiently compute potential moves without recalculating the offsets repeatedly. Together, these data structures ensure that the BFS is both systematic and efficient. Analyzing the complexity of this algorithm helps us understand its performance characteristics. For time complexity, the BFS explores all positions at increasing distances from the origin. Since each position has up to 8 neighbors, the total number of explored positions depends on the distance to the target. In the worst case, this results in a time complexity proportional to the number of reachable positions. However, the symmetry optimization significantly reduces the effective search space, improving practical performance. For space complexity, the queue and visited set grow proportionally to the number of explored positions. These data structures store information about the reachable area, which is determined by the target's distance. While both time and space complexity depend on the target's location, the algorithm remains efficient due to the dynamic and systematic nature of BFS. Finally, it is important to consider several edge cases to ensure the algorithm handles all scenarios correctly. If the target is at the origin, that is, x, y equals 0, 0, the shortest path is trivially 0 moves. Negative coordinates are naturally addressed by the symmetry optimization, which reduces all coordinates to their absolute values. This means the algorithm effectively operates in the first quadrant, simplifying the logic without loss of generality. For very large target positions, the BFS dynamically adjusts the search area, exploring only positions that are reachable. This eliminates the need for predefined bounds and ensures that even distant targets can be handled efficiently. These edge cases highlight the robustness and adaptability of the algorithm, making it well suited for the problem at hand. Here, we begin by importing the DEEC collection from the Collections module, which we will use for our breadth-first search, or BFS. Next, we define the min-night-moves function within the solution class. The first step in the function is to normalize the target coordinates, x and y, to the first quadrant. This is possible because of the symmetry in a knight's movement on a chessboard, allowing us to simplify the problem without losing generality. After normalization, we define all the possible moves a knight can make, represented as pairs of changes to the x and y coordinates. These moves capture the unique L-shaped movement of a knight. To implement BFS, we initialize a queue with the starting position, 0, 0, and a distance of 0. We also create a set called visited to keep track of positions we've already explored, starting with 0, 0. The BFS loop begins by dequeuing the current position and distance. If the current position matches the target, we know we've reached the destination, so we return the distance. Otherwise, we iterate through all possible knight moves to determine the next positions the knight can reach. For each move, we calculate the new position and ensure it hasn't been visited yet, while also applying a pruning condition to limit exploration to positions near the target. If the new position meets the conditions, we add it to the visited set to avoid revisiting the same node in the future. We then append this position, along with the updated distance, to the BFS queue. This continues until we either find the target or exhaust all possible moves. Finally, we include a safety return statement at the end of the function, returning -1 if no solution is found, though this should never occur given the constraints of the problem. Together, this implementation ensures we efficiently compute the minimum number of moves needed for a knight to reach the target position, leveraging both BFS and symmetry to optimize the process. To solve the minimum knight moves problem, we start by normalizing the target coordinates to the first quadrant. This is because the movement of the knight is symmetric across all quadrants, so reducing the problem to the first quadrant simplifies our calculations without losing generality. Next, we define all possible moves a knight can make on a chessboard. These are represented as an array of direction vectors, where each pair corresponds to the horizontal and vertical components of a move. For example, 2, 1 means moving 2 steps horizontally and 1 step vertically. We then set up a breadth-first search, BFS, to find the shortest path. A queue is initialized to manage our exploration, starting from the origin point, 0, 0, with an initial distance of 0. Additionally, we use a hash set to track visited positions and avoid revisiting them. This ensures we don't process the same position multiple times, which would lead to unnecessary computations. The BFS loop begins, and while the queue is not empty, we pull the current position along with the distance traveled so far. If we reach the target coordinates, we immediately return the distance as the result. Now, we explore all possible moves from the current position. For each direction, we calculate the next position by adding the direction vector to the current coordinates. We then generate a unique key for this position by combining the x and y values as a string. To optimize our search, we only consider positions that haven't been visited yet and are within a reasonable range near the origin, specifically greater than or equal to -2. This pruning step significantly reduces the search space, as positions too far from the origin are not relevant for reaching the target in the fewest moves. If the position is valid, we mark it as visited and add it to the queue along with the updated distance. The BFS continues until the queue is empty, but since we're guaranteed to find the target within a finite number of moves, we should never reach the fallback return statement of -1. This ensures an efficient and accurate implementation of the solution to determine the minimum number of knight moves required to reach the target coordinates. To solve the problem of finding the minimum number of moves for a knight to reach the target at 2, 1, we break it down into clear steps. First, we normalize the target coordinates, taking their absolute values. This is because the chessboard is symmetrical, and the problem can be reduced to the first quadrant without changing the result. So, x becomes 2, and y becomes 1. Next, we define all possible knight moves, which include 8 directions such as moving 2 steps vertically and 1 step horizontally, or vice versa. To explore the shortest path, we use a breadth-first search, or BFS. We initialize the BFS with a queue starting at the origin, 0, 0, with a distance of 0. We also maintain a set of visited positions to avoid revisiting the same squares. In the first iteration, we dequeue the starting position, 0, 0, and calculate all possible moves a knight can make. Among these, only valid positions, such as 2, 1, and 1, 2, are added to the queue with an updated distance of 1. In the next iteration, we process the position, 2, 1, which matches our target. Since we've reached the destination, we return the distance, which is 1. Now, let's consider the target, 5, 5. Again, we normalize the coordinates, so x and y remain 5. We define the same set of knight moves and initialize the BFS with the origin at 0, 0, distance 0, and an empty visited set. In the first iteration, starting at 0, 0, we calculate all possible moves. Valid moves such as 2, 1, and 1, 2 are added to the queue with a distance of 1. As we proceed through subsequent iterations, we continue the BFS process, dequeuing positions, exploring valid moves, and adding new positions to the queue while marking them as visited. The BFS ensures that we reach the target in the minimum number of steps, as it explores all positions at a given distance level before moving further. Eventually, we reach the position, 5, 5, and the corresponding distance, 4, is returned as the output. For the target, -4, -3, the process remains consistent. First, we normalize the coordinates, so x becomes 4 and y becomes 3. This allows us to reduce the problem to the first quadrant, leveraging the symmetry of the board. Using the BFS approach, we start at the origin, explore all valid knight moves, and continue to expand the search level by level. As in previous examples, we prune unnecessary moves by avoiding revisited positions, ensuring efficiency. Eventually, the target position, 4, 3, is reached in 3 moves. This is the minimum distance, and we return 3 as the output. To determine the time complexity of our solution, we start by analyzing the breadth-first search, or BFS, traversal process. BFS ensures that we explore all positions reachable within k moves before proceeding to those reachable in k+1 moves. This guarantees that we find the shortest path by traversing the graph level by level. The knight's movement essentially creates a graph where each position is a node, and each valid move leads to a neighboring node. Now, to make the search more efficient, we apply pruning strategies. By normalizing the target coordinates to the first quadrant, we reduce the exploration space significantly. Additionally, we restrict the search to positions where both next_x and next_y are greater than or equal to -2. This helps avoid exploring unnecessary positions. Finally, the search space is bounded by the Manhattan distance from the origin to the target, x, y. Since the knight's moves cover distances within fixed bounds, the total number of positions we may need to explore is proportional to O, x*y, where x and y are the target coordinates. To quantify this further, we can see that BFS explores each position in the search space at most once, thanks to the visited set that ensures no position is revisited. Each position has up to 8 potential neighbors, which is a constant factor. Therefore, for a target x, y, the total search space is approximately proportional to O, x*y. This gives us an overall time complexity of O, x*y. On the space complexity side, memory usage is primarily determined by 3 components. First, the visited set, which keeps track of all explored positions, can grow to include all positions within the bounded area, making its size proportional to O, x*y. Second, the BFS queue stores positions to be explored, and at its peak, it may contain all positions at a single BFS level, which is again bounded by O, x*y. Lastly, there are auxiliary data structures like the directions array and a few variables, but these require only constant space. As a result, the total space complexity is also O, x*y, dominated by the visited set and the BFS queue. When comparing the optimized BFS approach to a brute force method, the difference in efficiency becomes clear. A naive brute force approach would attempt to explore all possible sequences of knight moves, resulting in exponential time complexity of O, 8 to the power of k, where k is the minimum number of moves required to reach the target. In contrast, the BFS approach reduces the complexity to O, x*y, by systematically exploring only the reachable positions level by level while pruning unnecessary paths. Looking at different scenarios, the best case occurs when the target is very close to the origin, allowing BFS to terminate early. However, even in this scenario, the worst-case bounds of O, x*y, still apply. In average and worst cases, BFS will explore all positions within the bounded area, resulting in the same O, x*y, time and space complexities. To summarize, the BFS approach, with its use of pruning and symmetry, is significantly more efficient than brute force. It ensures that both time and space complexities remain proportional to the size of the bounded search area, making it a practical solution for this problem. When solving the minimum knight moves problem, there are several common mistakes to watch out for. First, avoid representing the board as a dense adjacency matrix. While this approach might seem intuitive, it can lead to excessive memory usage, especially for large boards. A better strategy is to treat the board as an implicit graph, where each position is a node and edges represent valid knight moves. Next, it's important to handle out-of-bounds moves properly. Neglecting this can result in runtime errors, so always validate moves before adding them to the queue or marking them as visited. Another frequent error is failing to mark visited nodes. By revisiting already processed nodes, you'll unnecessarily increase time complexity and risk infinite loops. Additionally, using DFS instead of BFS can be problematic for shortest path problems in unweighted graphs. BFS is more suitable here because it systematically explores all nodes at the current depth before moving deeper, ensuring you find the shortest path. Finally, generating knight moves inefficiently can introduce bugs and reduce clarity. Instead of hard-coding all possible moves, define them as reusable relative offsets, such as 2, 1, 1, 2, etc., which makes your code both cleaner and less error-prone. Now, let's discuss some key insights that are especially relevant for interviews. This problem is a classic example of a shortest path problem in an unweighted graph, making BFS the standard approach. Interviewers often evaluate your ability to implement BFS correctly and efficiently, so it's important to understand its mechanics well. Optimizations also play a crucial role. For instance, implementing early termination, where you stop the BFS as soon as you reach the target, can demonstrate your ability to refine solutions. Handling edge cases is another area interviewers may focus on. Be ready to explain how your code deals with scenarios like the start and target positions being the same, small board sizes like 1 by 1, or cases where the target is unreachable. Additionally, discussing trade-offs between different approaches can set you apart. For example, mentioning bidirectional BFS and comparing its complexity with standard BFS shows a deeper understanding of problem-solving strategies. There are also several related problems that can help you strengthen your BFS skills. For instance, LeetCode problem 994, rotting oranges, involves a similar grid-based BFS approach. Another great example is LeetCode 542-01 matrix, which focuses on finding the shortest distance in a grid. If you're looking for a variation of BFS that emphasizes paths over distances, LeetCode 126, word ladder 2, is a great problem to explore. For an even more challenging BFS application, LeetCode 773, sliding puzzle, introduces additional constraints while working with a grid. Solving these problems can deepen your understanding of BFS and its versatility across different scenarios. Lastly, there are alternative approaches worth considering for the minimum night moves problem. Bidirectional BFS is one such method. Instead of exploring from the start position alone, you can simultaneously explore from both the start and target positions, effectively reducing the search space. However, this approach requires careful bookkeeping to track visited nodes from both sides. Another option is a asterisk search, which incorporates a heuristic, such as the Manhattan distance between the current position and the target. A asterisk can prioritize more promising paths, potentially speeding up the search. That said, designing the heuristic is critical to ensure optimal solutions. Finally, for fixed-size boards, dynamic programming can pre-compute the shortest paths for all possible start-target pairs. While this is highly efficient for repeated queries, it's impractical for large boards due to the significant pre-processing time and space requirements. Understanding these alternatives can help you adapt your approach to different problem constraints and contexts. Great job exploring the solution. To summarize, we used BFS to efficiently calculate the minimum night moves, taking advantage of symmetry to reduce the search space. Remember, BFS is a go-to choice for unweighted shortest path problems. Thanks for watching, and be sure to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!